We're pleased to welcome Jennifer Schultens joining us at before 7 a.m. her time. Thank you, Ken, for that. But she will tell us about flipping Heegaard splittings.
Thank you. Yes. I'm glad I'm here. I'm glad I'm awake enough to have figured out how to share the screen on my beautiful new laptop. I won't name any names, right? Okay. And I'll be talking about flipping Heegaard splittings. I think if I understand correctly, if I was really in Miami, I would probably be talking about flipping condos or something, because that's a more lucrative endeavor. But alas, I will be talking about flipping Heegaard splittings. So many of you, oh boy, yeah. Those of you who've known me for a while, and maybe some others of you have seen much of this before. These are things I like to talk about and think about, or have been for some time now. And so hopefully this will just be a chatty talk. I think I have more or less a comprehensive theorem, but definitely not quite. So there's room for improvement. Ideas are definitely appreciated. And so first off, I'll just sort of go over the basics of Heegaard splittings, because not everybody has seen me talk about this for 2 decades or more. And then I'll talk about flipping Heegaard splittings, what it means. This is sort of a somewhat newer thing that people have been thinking about, especially as it relates to the Gertz group. And so Gertz group of a 3-manifold is something I've been thinking about a little bit, but nothing definitive yet. And then I will talk about stabilizing Heegaard splittings. Again, that's something I've thought about for a while. And it's also the context in which flipping Heegaard splittings was first discussed. And then finally, I'll finish by talking about probably my favorite class of 3-manifolds, namely ciphered fibered spaces. I'll talk a little bit about what they are, and also about the structure of Heegaard splittings and what that tells us about flippability of Heegaard splittings. Okay, I think more or less in this talk, everything is orientable. If you do happen to spot a manifold that's not orientable, just let me know. I think there might be 1 or 2. But otherwise, assuming that everything is orientable makes things a little bit easier. Okay. So again, many of you have seen a lot of this before. I hope it's still interesting. I enjoy going back and reflecting on these things I've been thinking about for a long time. And so first of all, a handle body, a very special type of 3-manifold. Just think of it as a 3-dimensional regular neighborhood of a graph. So especially just a wedge of circles. Examples are 3-ball, solid torus, solid genus 2, solid genus 3, et cetera, et cetera. There's an example. That is a handle body of genus 2. It's meant to be a solid object. These are our basic building blocks today. And then a Heegaard splitting of a 3-manifold is a decomposition of the manifold into 2 handle bodies. 2 handle bodies then meet along their boundary. People have a lot of ways to draw this. There's very clever ways of keeping track of Heegaard splittings, encoding them. I tend to think about them more topologically, about, a surface that's floating around in my 3-manifold. And one thing that's important, especially today, is that we consider Heegaard splittings equivalent if their splitting surfaces are isotopic. So I'll mention my favorite examples, and then I'll talk about flippability, and I'll go over the same examples again. So again, most of you have seen these examples, but I want to think about them a little differently as well. But first, just the most basic example of a Heegaard splitting is the splitting of S3 into 2 3-balls, right? Each 3-ball is a genus 0 handle body. And so here is S3, a 3-manifold that has been split into 2 handle bodies that meet along their boundary. If you think of S3 as the unit 3 sphere in R4, then you know that there's an upper hemisphere and a lower hemisphere. So the splitting surface would just be the intersection of S3 with, say, the XY plane, XYZ plane, the space, sorry. And then the upper hemisphere would just consist of those points where the fourth coordinate is positive, and the lower hemisphere would consist of those points where the fourth coordinate is negative. Okay, so that's the standard genus 0 Heegaard splitting of S3. It's unique, right? Schultens and so forth. Okay. So that's an example we'll come back to in a moment. And then another Heegaard splitting of the 3 sphere is the splitting of S3 into 2 solid tori. Those are both genus 1 Heegaard splittings. One way to think about this when you're thinking just in the 3 sphere is to realize that if you take the Whitehead link, this one, and just fill up, make both components fatter and fatter and fatter, they fill up space. And then that's what you have. That's the genus 1 Heegaard splitting of S3. Another way to think of it is to think of, again, of S3 as the unit 3 sphere in R4. And then you have 4 coordinates, x squared plus y squared plus z squared plus w squared equaling 1. And you can think of the first 2 coordinates, x squared plus y squared equaling 1/2, and then z squared plus w squared also equaling 1/2. And so you get a circle's worth of circles. That would be the splitting torus of S3 thought of in R4. And when you think of it that way, you realize that just taking the inside of that, not unit circle, but circle of radius 1/2 in the XY plane, right? All of those points correspond to a point in S3. The Z and W coordinates would have to sort of add up to give you, right, norm 1. And then you can also flip it and say, oh, and then you take the points inside the circle of radius 1/2 in the ZW plane. And that divides S3 up into these 2 solid tori. It's somewhat helpful to think of that in this context later on. Okay, so genus 1 Heegaard splitting of S3, again, one of my favorite examples of a Heegaard splitting. And then one I've thought about in the last 2 years or so is S1 cross S2. People tend to prefer to say S1 cross S2. I think that is the right way to think of it, although I often say S2 cross S1. Okay, and then if you look at that second coordinate, that second factor, that's S2, right? That's a 2 sphere, so you can split it into northern and southern hemisphere again. And then each of those disks cross S1 is a solid torus. And so that's a Heegaard splitting of S1 cross S2. Okay, every 3 manifold, every compact 3 manifold admits a Heegaard splitting. You can generalize that as well. This was proved by both Bing and Moise. And in a sort of introductory course on 3 manifolds, it's a great thing to look at. There's 2 different ways to prove this. One uses triangulations, one uses Morse functions. Okay, so let's think about flippability. When we're thinking about flippability, the point is that we think of not just the splitting surface, but also the order in which we are listing the handle bodies that our manifold is being divided into. So M equals V union W along S, right, is ordered. V comes first, W comes second, and in an ordered Heegaard splitting, the point is that we consider 2 such things to be equivalent. All right, you have M equals V union W along S, and you have M equals V prime union W prime along S prime, and you want to isotope V into V prime, S into S prime, W into W prime. That's what equivalence means when we're looking at ordered Heegaard splittings. So you don't want to flip them, except we consider the Heegaard splitting to be flippable if the 2 ordered Heegaard splittings, where we list the handle bodies in the reverse order, if those are equivalent, right? In other words, if there's an isotopy that takes V to W, S to itself, but orientation reversed, and then W to V. That's what it means for a Heegaard splitting to be flippable. And so let's think about the examples we just saw. The first was the genus 0 Heegaard splitting of S3. And when you think of it in terms of that picture in R4, right, northern hemisphere, southern hemisphere, then you realize that you can rotate S3, let's say, in the XW plane, right, that last coordinate. And that takes the northern hemisphere to the southern hemisphere and the southern hemisphere to the northern hemisphere. Okay, so the genus 0 Heegaard splitting of S3 is flippable. Okay, and I'm just saying rotation of 180 degrees, right? Some axis, but just as long as the W coordinate flips. Okay, and then there's the genus 1 Heegaard splitting of S3. And there, I think I like, well, actually, if you can visualize Whitehead link getting very fat, then I think you can also probably visualize the components sort of being isotoped one into the other into the one, and that would flip the Heegaard splitting. Or if you actually like to think of it in terms of the coordinates more or less in R4, then you can also say, oh, the solid torus on the left, that was where x squared plus y squared is less than or equal to 1/2. And the solid torus on the right, that's where z squared plus w squared is less than or equal to 1/2. And if I rotate things in R4 so that the x and z coordinates are interchanged, and so that the y and w coordinates are interchanged, then I will be taking the solid torus on the left to the solid torus on the right, and vice versa. Okay, so the genus 1 Heegaard splitting of the 3-sphere is also flippable. Okay, and then this example, when you think about it, S1 cross S2, there in the second coordinate, we said we have that 2-sphere and you have a northern and southern hemisphere. Northern hemisphere, say, is the solid torus on the left. Southern hemisphere corresponds to the solid torus on the right. And then in that factor, right, you just rotate S2, flipping the northern hemisphere to the southern hemisphere and vice versa. And that isotopy extends across the S1 factor. Okay, so just the standard Heegaard splitting of S1 cross S2 is also flippable. The reason I like to mention it, I guess, is because for many years I avoided these reducible manifolds, and now I've warmed up to them. So there it is, a flippable Heegaard splitting of S1 cross S2. So at this point you say, oh, all of these examples have flippable Heegaard splittings. Now I should convince you that there are also other Heegaard splittings, those that are not flippable. So let me try to describe one of them. And I won't talk about Seifert fibered spaces very much right now. I'll do that a little bit later. But this is a nice first example to think of if you've never thought about Seifert fibered spaces. There are what are called small Seifert fibered spaces. And for now, oh, this picture has too much on it. Really, I just wanted a sphere here and 3 dots. That's all I really want in this picture. Because a small Seifert fibered space is a 3-manifold that you can get as follows. You start with a thrice punctured sphere. So here's your sphere, 2-sphere, thrice punctured 2-sphere. And so imagine these dots not being there, right? There's a boundary component there, a hole. And then you take that cross S1. So a thrice punctured sphere cross S1, that's certainly a 3-manifold. And now you do some Dane fillings along those 3 torus boundary components that you get. Okay, so thrice punctured sphere cross S1, and then Dane fillings. There'll be sort of 3 curves that are very interesting. And there's a sort of natural projection map that we'll talk about in a moment. That's why I'm drawing this spherical picture. So that is an interesting 3-manifold. It's called a small Seifert fibered space. And there's a very natural way to construct a Heegaard splitting on this small Seifert fibered space. Namely, we take two of the solid tori that came in through the Dane filling and then connect them up by sort of an unknotted horizontal arc in the thrice punctured sphere cross S1 part. Okay, that's a genus 2 handle body, right? Two solid tori with a flattened arc. And then what's important to realize is that the complement of that is also a genus 2 handle body. Namely, right, we have these two solid tori that we filled in, and then this arc sits inside an annulus, arc cross S1, which we should fatten up a bit. And then in that annulus, fattened up annulus, what we should realize is that the arc is kind of half of that fattened up annulus, and then the other half is also sort of a dual handle. That's what's indicated here, right? And if we took out, right, if we hadn't filled in those two solid tori and we took out that annulus, then we would just have a regular neighborhood of this other solid torus that was put in there through the Dane filling. And so solid torus plus that sort of dual handle, also a genus 2 Heegaard splitting. In this case is actually a really good warm-up case for how to construct Heegaard splittings on Seifert fibered spaces. Again, I'll talk more about those in a moment. But the point is, the reason these are interesting is that when I just did this construction, I kind of chose the two Dane filling tori on the left, and I didn't choose the one on the right. Okay, so that was one genus 2 Heegaard splitting that I got. But I could have chosen like the Dane filling torus on the left, the one on the right, done a similar construction, or I could have chosen the two Dane filling tori on the right and done the same construction. And so that gives me 3 different Heegaard splittings. And as long as there's nothing funny going on with the Dane filling sort of invariance being the same, those are actually distinct Heegaard splittings, non-isotopic Heegaard splittings. In fact, those were some of the first examples, right? Small Seifert fibered spaces were the first example of a 3 manifold that exhibited non-isotopic Heegaard splitting. So they're interesting in that way. And the way to tell them apart was through a certain invariant called Nielsen equivalence, which I'll discuss briefly later. And the fact of the matter is that those techniques also show us that this invariant is different for the handle body that I constructed here on the left and the handle body I construct on the right. And that means that this Heegaard splitting can't be flippable.
Jennifer,
Okay. Yes.
question.
Uh-huh.
Hi, this is Dave Peter.
Hi.
Can you just, is it possible to conclude that it's not flippable just because the handle body on the left contains 2 singular fibers and the handle body on the right contains 1 singular fiber, and those are kind of a inherent feature of the Seifert fiber space?
You know what, Dave? Yes, I'm working on that. So the answer is hopefully yes, not quite. You can't conclude it immediately, but I'm working on sort of precisely that, because there's in the 1 or 2 missing cases that I can't quite handle in terms of, well, I'll mention this later on, in terms of saying that certain vertical Heegaard splittings aren't flippable. If I did have a theorem like that, then I'd be able to just deal with every single case. But it's not quite that simple, right? I mean, somehow, yes, that's my gut feeling too, but I don't yet have a theorem to express that.
Is it straightforward to say what goes wrong, or is that too far?
Is it straightforward to what?
To say what goes wrong with that plane?
Yeah. Oh, here, I mean, here you can actually, yeah, but I'll talk about this a little bit more later, but yeah. I mean, it is just that you really, I mean, this goes back to work of Lustig and Moriah, however you want to pronounce his name, about Nielsen equivalence of generating systems of Fuchsian groups, right? And so they have all those calculations. And so what you're kind of aiming at is a much stronger theorem, or let's just say a more definitive theorem in this context, where you say, if you have an exceptional fiber in one of the handle bodies, somehow that's like some sort of non-primitive curve that exists, and it would exist in one handle body, but in the other. But again, I haven't been able to really nail it down to express that in a mathematically rigorous way. Okay, so if you have ideas, yeah, we can talk about this. And I'll mention my sort of missing case too. Okay, so I wanted to talk about some other things before I get back to that. Okay. So these were unflippable. Okay, I wanted to talk a little bit more about where people first started wondering about or thinking about flippability. So we mentioned the genus 1 Heegaard splitting of S3. It is one of my favorites for several reasons. Mainly because when you take a pairwise connect sum, you have a 3-manifold Heegaard splitting, and then you take a pairwise connect sum with S3 and the genus 1 Heegaard splitting, that gives you a new Heegaard splitting for the same manifold, right? The manifold you just take and connect sum with S3, so that hasn't changed, but the Heegaard splitting is now a new Heegaard splitting that has a higher genus. And so that process is called stabilization. Right? Take a handle body. You're just adding a handle. That's what it looks like. And in the complementary handle body, it looks the same. And there's a theorem that says that given any 2 Heegaard splittings of a 3-manifold, they become equivalent after some sequence of stabilizations. So that's a famous theorem by Reidemeister and Zinger. Again, good sort of exercise in the literature. You can prove this via triangulations, barycentric subdivision, and so forth, or by the work of Cerf. Oh, and this is just a somewhat gratuitous example that I think is really cool. Nothing particularly to do with what we're talking about today, but Cassidy and Gordon, just in terms of interesting phenomena of stabilized, unstabilized. Cassidy and Gordon produced a sequence of manifolds with Heegaard splittings of infinitely high genus, right? Each of these manifolds has many, many Heegaard splittings. In fact, there's no bound on like the genus, how high the genus is within the family of manifolds and how many Heegaard splittings they have. Anyway, just a cool example. The problem I've thought about more is the stabilization problem. So something I proved a while ago, I'm not mentioning it, writing it up down here as a theorem, but it is a theorem, is that for Heegaard splittings of ciphered fibered spaces, again, I'll talk about them more in a moment. For Heegaard splittings of ciphered fibered spaces, if you take the higher genus Heegaard splitting, right, you have 2 of them, you take the higher genus Heegaard splitting and stabilize it just once, and then stabilize the other Heegaard splitting enough to achieve the same genus, then those 2 would have to be isotopic. And so the stabilization problem asks, how many stabilizations are necessary, right? Given a 3-manifold, given 2 Heegaard splittings, how often do you have to stabilize in order for the 2 to become equivalent? The Reidemeister-Singer theorem says that after some number of stabilizations, the 2 become equivalent, but the question is, what are bounds on it? And so Rubinstein-Charlemagne did some fantastic work about this, where for non-Haken 3-manifolds, they established a sort of linear bound in terms of the genera of the 2 Heegaard splittings. And then, by the way, for non-Haken manifolds, they established, a quadratic bound in the genera of the Heegaard splittings to say that's the top number, the highest number of stabilizations you could possibly require. But then for many years, there was this huge gap between the established upper bound, right, coming from Rubinstein-Charlemagne, probably could be improved, is something to look at again. And then the lower bound, the examples known, in the examples known, all that was ever required was 1. So for a while, people were actually conjecturing that 1 was always enough. Okay, and that turned out not to be true. This was a result by Haas, Thompson, and Thurston. They created constructed a family of 3 manifolds with 2 genus G Heegaard splittings that required G stabilizations to become equivalent, right? So in other words, this family gives you Heegaard splittings where if you want to say, oh, you need 5 or more stabilizations, then you say, oh yeah, take the ones that have genus 5 or 100 or 1,000,000, right? There's no upper bound to how many stabilizations are necessary. And in fact, though, these 2 genus G Heegaard splittings were exactly a Heegaard splitting and its mirror image, right? So a Heegaard splitting and its mirror image, right? V union W along S and W union V along S, those 2 Heegaard splittings in these manifolds require G stabilizations. If you take 2 copies of the surface, just parallel, and then sort of tube them together, that gives you a Heegaard splitting, always, anytime, right? And that Heegaard splitting will be a stabilization, both of a Heegaard splitting and of its mirror image, okay? And so what Haas, Thompson, and Thurston did is to show that in the manifold they constructed, that's the best you can do. There will be no lower genus Heegaard splitting. That's a stabilization, both of the Heegaard splitting and its mirror image. And the point was then that those Heegaard splittings are certainly unflippable, right? The methods they used were very analytical. They looked at harmonic maps. And then Jesse Johnson sort of looked at those manifolds, meditated deeply the way he always did, and boom, he saw the topology in it and managed to sort of prove the same theorem, but just purely topologically. And in the process, he introduced what's called the flip genus. So how often do you need to stabilize, given a Heegaard splitting, how often do you need to stabilize in order for that Heegaard splitting to become isotopic to something that flips, that's flippable? Very nice paper. I think Jesse Johnson's work deserves to be reconsidered and so forth. There's still a lot of unfinished business there. And so let me talk a little bit more about Seifert fibered spaces and go into a bit more depth than I did before. Okay. So if you have a cylinder, right, disk cross an interval, you have point cross interval, points cross interval, that's a fibration. And then if you rotate through, an angle of what, or let's say, what's the convention? 2 pi times P over Q or Q over P, and then identify, then you get a fibered solid torus. A fibered solid torus. So if you just identify via the identity map, then you have a product fibration, just point cross S1. But if you rotate, so notice, right, through a rational angle, then the fibers wind around the central fiber. Central fiber, midpoint, right, that's identified to itself. That's the central fiber, but the other ones will wind around it, and they'll wind around it sometime and also go around the other direction. Okay, so that's a fibered solid torus. And then a Seifert fibered space is a compact 3 manifold that is the union of disjoint simple closed curves, each of which possesses a fibered solid torus neighborhood, right? So your whole 3 manifold decomposes into simple closed curves. Fatten any of those up, you will see a fibered solid torus neighborhood. In most cases, right, and then think about if you have one of these central fibers that other fibers are winding around, then those other fibers, if you look closely at them, just have a product neighborhood. So each of these simple closed curves is called a fiber, right? And most of those fibers will be called regular because their fibered solid torus neighborhood is a product, but then some of them are exceptional. And just again, if you think of a fibered solid torus neighborhood of an exceptional fiber where other fibers are wrapping around it, you realize that those are isolated. And because we started out with a compact manifold, and each fiber has a fibered solid torus neighborhood, it means that there's only finitely many exceptional fibers. Okay, so this is your three-dimensional Seifert fibered space, all of these sort of fibers sort of lining up mostly, sometimes winding around each other. And what you need to realize is that you get a natural projection map that maps each fiber to a point. Each fiber is just mapped to a point. And if you look at your fibered solid tori, right, you realize that your projection map away from the exceptional fibers, you're definitely just going onto a surface, right? The disk cross S1, you have fibered solid torus is just a product, so you're going to just a disk. And then near the exceptional fibers, your fibered solid torus neighborhood is actually also going to disk. I will go backwards for a second here. You should think of this solid torus as being sort of separated into sectors. And then when you do your identification, right, you kind of take one of these sectors and kind of wind it around and it attaches to one of the other sectors. So when you quotient each fiber to a point, you're also getting a disk. Topologically, geometrically, you're getting a cone. And so when I draw my draw the projection, which I'm calling the base orbifold, I like to draw these cone points. These points here correspond to exceptional fibers. So I think what I like about Seifert fibered space and what other people like about them too is that because of this fibered structure and because of this natural projection map, it's as if you're living in a 2+5 dimensional space, right? Yes, there's a 3 manifold, but also there's so much you can just encode in this 2-dimensional base orbifold. And so as long as I make all of my orientability assumptions, my base orbifold will be some sort of surface with a couple of these cone points. Again, the cone points correspond to these exceptional fibers. And so sometimes we even want to make a note of sort of the number of times that regular fibers wrap around an exceptional fiber, and then you would actually write the number here and say, oh, 3 nearby regular fibers wrap 3 times around this exceptional fiber. Okay. So when we have one of these Seifert fibered spaces now, there's a standard construction of what are called vertical Heegaard splittings. Vertical because the motivation is to take some of the exceptional fibers, right? Take regular neighborhoods of those. Those are solid tori, and then you want to soup things up so that that gives you a handle body, and you want to ensure that the complement is also a handle body. So, okay, here's a picture from a paper of Yoav Morai and myself. You can, in the picture I had earlier, I just drew, right, I had a small Seifert fibered space. So now that we know a little bit more about Seifert fibered spaces, we can think back and say, oh, so I had described it in terms of thrice punctured sphere, crosses 1, then Dane fillings. Okay, that's fair enough in that example. But now you also say, oh, and then we can look at that 3 manifold and project each fiber to a point. And that gives us a 2 sphere with 3 of these cone points, right? That's our base orbifold. And then there, the way I constructed my first example of a vertical Heegaard splitting was to say, oh, I choose 2 of those exceptional fibers, fatten them up, then take a little horizontal arc, that gave me a genus 2 Heegaard splitting. And the complement of that, sorry, that was a genus 2 handle body. And the complement of that was also a genus 2 handle body. Okay, here, pardon me, this is actually not quite the schematic I need. This is more of a question of how you compute the fundamental group. There's a relation, sort of an interesting relation, somewhat subtle, complicated relation between fundamental group and handle bodies in the manifold. What we actually want to do is, let's say we take these 3 points that we see here. Those are, let's say, cone points coming from exceptional fibers. And those, I will simply, I'll just take the whole fibered solid torus neighborhood, and I'll want that to be in one of my handle bodies. And so that's fine. Just connect them up via some horizontal arcs. Great. But then the complement will not be a handle body. And so you need to throw in a few more horizontal arcs to guarantee that the complement of the handle body you constructed is also a handle body. Okay, so I just gave you a taste of how I think about Heegaard splittings, right? I take a manifold and I'm trying to fill up space. I'm building one handle body inside the manifold, but then I need to make sure that the complement is also a handle body. Okay, and so again, motivation, just take the fibered solid torus neighborhoods of some of the exceptional fibers, right? A sub collection, not all of them. And you can, so there's lots of different choices. That's why Seifert fibered spaces have typically many non-isotopic vertical Heegaard splittings, but then throw in a bunch more, first of all, horizontal arcs, fattened horizontal arcs to connect the thing up, but then also to sort of carve out the complement so that what remains after you do this is also a handle body. Okay, so that is definitely a construction for Heegaard splittings in a Seifert fibered space. They're called vertical Heegaard splittings. There's typically many of them. They're distinguished through this work on Nielsen equivalence. One moment, that is not where I wanted to go right away. Sorry, I think I have things a little bit backwards. Oh, okay, no, sorry. All right. But then, as it turns out, there's another construction for Heegaard splittings and Seifert fibered spaces. And this one doesn't always work. And this schematic doesn't tell you the whole picture either. Okay, but I'll tell you what it represents. So vertical Heegaard splittings, and here's the other construction, horizontal Heegaard splittings. So notice here, this thick black interval, that is supposed to be an exceptional fiber. And what you're thinking about is this exceptional fiber sitting in the 3 manifold. Oh, by the way, it can also be a regular fiber. The question is just whether this construction works or not, whether in fact it gives you a Heegaard splitting or whether it just tells you this doesn't work. Okay, so you start with a fiber. So maybe you should think of this vertically or something. And then you say the complement of a regular neighborhood of that fiber is a Seifert fibered space with a boundary. There's one torus boundary component, right? For the rest of all of this, we were thinking of closed 3 manifolds, closed Seifert fibered spaces. So now we have removed an exceptional fiber, we've removed a regular neighborhood of it, and so we have a torus boundary component. And then you can either try to construct this directly or use some algebraic topology to see that Seifert fibered space with boundary fibers in the other direction. It is also a surface bundle over the circle, a mapping torus, right? So this sort of complementary manifold now, complementary to regular neighborhood of that fiber is a mapping torus. And so you could just take 2 copies of that fiber surface from the mapping torus and say, oh yeah, so this complementary manifold decomposes into punctured surface cross interval, punctured surface cross interval. those are handle bodies, but they're not filling up the whole Seifert fiber space. Now I still need to put back in the regular neighborhood of this fibered solid torus neighborhood of this fiber. And then the question is, when I put that back in, I'm sort of smushing it onto one of these handle bodies. Right, and the two handle bodies I'm referring to are just surface cross interval, right? So you have to imagine the annulus along which this fiber, the neighborhood of the exceptional fiber meets that handle body. There's some sort of annulus, right, corresponding to boundary cross interval. And you're just putting that solid torus in there. And if this fiber, right, if this solid torus that you're smushing onto that handle body along that annulus, if it's primitive, then you end up with a handle body. And so that's this very special situation. You have to calculate whether or not that works out in terms of this mapping torus structure, right? Boundary of the fiber surface for the mapping torus. What's the, what are the coordinates for that? How does all of that work out? If it all works out, that you're gluing that solid torus in such a way that it's primitive, then you get this horizontal Heegaard splitting. But again, very special situation. Sometimes it works. It's interesting when it works, when it just doesn't work. Interesting phenomena associated to that. All right, but keep this in mind that this horizontal Heegaard splitting comes from having a mapping torus, right, which can sort of be rotated so that the two parts are interchanged. Cross interval, surface cross interval, right? Just rotate by, well, 180 degrees. That interchanges those two sides. And then rather than smushing the solid torus onto one of those, you can just kind of divide it down the middle, smush it onto each side. That's a horizontal Heegaard splitting. And I have also hopefully just convinced you that it is flippable. And so that's what's interesting about horizontal Heegaard splittings. They're maybe not very common if you can quantify that, but they are flippable. Okay, and then Yoav and I proved this result some time ago that irreducible Heegaard splittings of Seifert fibered spaces are either horizontal or vertical. So again, horizontal only in very small percentage of cases, and then usually vertical. And so this is sort of a natural arena for me to say, oh, are they flippable or not? And then let me say a few words about this technique that works to show that certain Heegaard splittings are not flippable, or just more generally, certain handle bodies are not isotopic. And so this is this idea of Nielsen equivalence. The fundamental group of a handle body is a free group. And moreover, if you have a Heegaard splitting, right, you've divided your three manifold up into two handle bodies. So if you look at one of those handle bodies, its fundamental group is a free group. And moreover, it gives you a generating system for the fundamental group of the three manifold, right? Start with one of the handle bodies. Just thinking through Seifert Van Kampen, right? You have a generating system coming from that handle body, just the fundamental group of that handle body, a free group, and then you're attaching the cocores of the handles of the other handle body in order to actually get the relations for the fundamental group. But the important thing is, if you're looking at a handle body that's a handle body in a Heegaard splitting, then that gives you a generating system for the fundamental group. So that's where this idea of Nielsen equivalence becomes interesting. Because if you isotope that handle body around in the manifold now, then that generating system might, is still sort of, it's the same in some way, right? But in terms of other data you're getting from the three manifold, you might be writing it differently. However, the amazing thing coming from this work of Nielsen is that there are sort of moves on these generating systems you can do that tell you whether or not those things are Nielsen equivalent. So whether or not those two generating systems can possibly be coming from a handle body that's been isotoped around in the 3-manifold. I mean, Nielsen's work pertains to other arenas as well, but for someone like me who's interested in 3-manifolds, Heegaard splittings of 3-manifolds, isotopic handle bodies around, that's what it amounts to, right? So let's say you have two generating systems. And if you go back to the picture I had of a horizontal Heegaard splitting, when I choose those exceptional fibers and then throw in these other curves, in terms of the data, the presentation of a fundamental group I have for the Seifert fibered space, that choice of exceptional fibers and that construction of the Heegaard splitting gives me a generating system for each of the handle bodies in the Heegaard splitting. And it gives it to me in terms of certain data coming from the Seifert fibered space. And so let's say I have a vertical Heegaard splitting here, another vertical Heegaard splitting here, or just one handle body in the vertical Heegaard splitting and the other handle body. And I write down those generating systems and the Nielsen equivalents or the Nielsen elementary Nielsen transformations are just switching X1 and X2. Right, in your handle body, yeah, I mean, there's several solid torus summons, so which one you write first doesn't matter, right? Cyclically permuting, same idea, right? It doesn't matter in what order you would write those. Also, replacing a generator with its inverse, right? That's just going around a handle one way or the other way. Or this one is probably the most interesting in this context. Replacing a generator with a product of it with something else, right? If you have a handle body sitting in a 3-manifold, you can take a handle and slide it over itself. And then these are the elementary transformations, but two generating systems are Nielsen equivalent if one can be obtained from the other through a sequence of these elementary transformations. So that's pretty rigid. And here's what I was saying about free fundamental group and how we get a generating system out of a handle body in a Heegaard splitting. And then if a handle body can be isotoped into another handle body, right? For instance, into the other handle body in a Heegaard splitting, then the generating systems we get need to be Nielsen equivalent. And theorems of Lustig and Mariah on Nielsen equivalence of generating systems for Fuchsian groups distinguish between vertical Heegaard splittings, and they also distinguish between the two handle bodies in the Heegaard splittings. More or less, there are cases that are missing. So number one, one moment. Oh, right. So in a Seifert fibered space, when you look at the exceptional fibers, typically your invariance for different exceptional fibers will be different. But of course, in sort of unusual cases, they'll actually be the same, right? And so then these techniques by Lustig and Mariah don't actually tell you whether or not these are the vertical Heegaard splittings that you get by choosing distinct collections of exceptional fibers to construct the vertical Heegaard splitting, whether those are the same or different. And they also don't tell you anything about flippability. So for instance, in the case of a small Seifert fibered space, right? If you have, well, there you'd have, or let's say you have a bigger Seifert fibered space. It's fibered over the 2-sphere, 4 exceptional fibers. And like pairwise, they have the same invariance. And then you take one of each class of invariance and pick an exception fiber with that, connect those up, construct a vertical Heegaard splitting that way, right? Maybe it's flippable, maybe not. My guess is it's not flippable, but I can't prove that because sort of more or less the only technique I have to distinguish between a handle body before and after an isotopy would be the Nielsen equivalence. And if the invariants are the same, then these techniques don't allow me to distinguish between the two. So there's still a little work to be done. And then
There's a
oh,
comment from
oh,
Ian
chat.
that popped up on the chat. Do you need me to read it out to you, or do you see it? Can you read it out?
Yeah. Yeah, that should be right. Yeah, Ian, that's right. And so,
Sorry, we don't have the chat visible here. Let me.
yeah. So.
Don't
so
you need to allow
Ian was
conjugation
saying-
in the fundamental group as well as
Yeah.
Nielsen equivalents, since isotopy between Heegaard splittings
Yeah.
might not preserve a base point?
Yeah, that's right. That's right. That's absolutely true. And then maybe it deserves to be pointed out that the reason Lustig and Mariah are actually looking at Fuchsian groups is because they're not actually looking at the whole fundamental group of the Seifert fibered space. They're actually modding out by that normal subgroup, Z subgroup. And then I'm thinking, does that change much? I mean, they did all the hard work, right? I have not dug into the details, but you're right. They do look at that. They do allow conjugation. That's right. Sorry. So I should have put that up as one of my allowable moves. Is it an elementary Nielsen transformation? I think it's not called that, but we certainly allow it. And then in the work of Lustig and Mariah, they also account for conjugation. That's true. Yes. Does that answer your question fully? Okay. All right. Oh, and I just want to mention one other case. So Lustig and Mariah, like I said, they did a lot of the hard work of distinguishing generating systems for coming from Heegaard splittings for Seifert fibered spaces, vertical Heegaard splittings of Seifert fibered spaces, where their work makes sense and allowing for conjugation. But they require either positive genus for the base orbifold or two or more exceptional fibers. No, sorry, they always require two or more exceptional fibers. And so the one case I can't handle, and this goes back to Dave Fuder's question that I don't know the answer to, or kind of conjecture the answer is yes to, is what happens if you have a vertical Heegaard splitting that of a Seifert fibered space where you just have one exceptional fiber? So if you just think of surface cross S1, if you have surface cross S1, then there's a standard Heegaard splitting that has genus 2G plus 1. It's the unique standard Heegaard splitting, and it is flippable because you can just kind of move it up and over, so to speak. If you think of, there's another way to think of constructing it, namely just as surface cross as interval, and the amalgamation of two such Heegaard splittings. And that is the same as thinking of it in the more standard polygonal picture, which some of you might know about. And then when you think about it in this surface cross I picture, then it's clear that you can just kind of rotate it through the S1 factor. And so it's flippable. Okay, but now take that three manifold and take one of the vertical fibers, maybe the one where you've actually attached the vertical handle, right? In the polygonal picture, take that one of those vertical edges and do a Dane surgery there. And now you have a Seifert fibered space with one exceptional fiber, and this rotation picture doesn't work anymore. So maybe it's still flippable for other reasons, and maybe not, right? And the reason I don't know is because the construction I know doesn't work. And then these techniques of Lustig Mariah break down. So personally, I'm kind of trying to look at Nielsen equivalence a little more closely to see whether I can sort of look at that fundamental group specifically to say, yes, the handle body containing the exceptional fiber, or what I want to say is the handle body containing the exceptional fiber and the one that doesn't contain the exceptional fiber are somehow structurally different and can't possibly be isotopic, right? But it really requires going down into sort of the heart of the matter in terms of Nielsen equivalence. At least that's the only technique, the sort of approach I envision to sort of say, confirm this conjecture that the two would be different, right? Okay, then maybe one moment. So for reasons of the inequivalence of Nielsen of generating systems. Vertical Heegaard splitting is not usually flippable, possibly never. Horizontal Heegaard splittings are flippable.
What does usually mean?
It means that they're not flippable, but I don't know whether or not they are in these a couple of situations, namely. Okay, so I don't know whether or not, so most Heegaard splittings, what does it mean? What does it mean? Okay, so you have all of your, you have your ciphered fibered space, and then if you have two or more Heegaard splittings, two or more exceptional fibers, pardon me, and all of them have distinct invariants, then the Heegaard splittings will not be flippable. If, in fact, as long as the set of exceptional fibers doesn't break into two collections with the same number and with corresponding invariants, Heegaard splittings will not be flippable, assuming you have two or more exceptional fibers. Okay, so if you just have one exceptional fiber, I don't know if the Heegaard splitting is flippable. I'm conjecturing it's not, but I don't know the answer. Okay, so visually. And then also, if you have an even number of exceptional fibers, right, that's partitioned into two groups where the invariants correspond exactly, then I also don't know whether or not the Heegaard splitting is flippable. Okay, so there's those sort of exceptional cases where I just don't know whether or not it's flippable. So maybe I shouldn't even state the theorem. I mean, that usually means it's not quite a definitive theorem yet. It's not quite done. There's a little work to be done. Or maybe there's just some technical exclusions one needs to state, which I didn't do yet. Okay, does that answer your question?
Yes, thank you.
Okay, all right. And then horizontal Heegaard splitting is always flippable. And then the one other thing that I don't want to talk about open book decompositions, but open book decompositions, when manifolds have open book decompositions, there's also a notion of horizontal Heegaard splitting, and those would always be flippable for the same reason, actually for an even simpler reason. Okay, but then the one other thing I want to say is that thinking back to my work on stabilized Heegaard splittings of ciphered fibered spaces, and the sort of isotopies I managed to perform there, if you take a vertical Heegaard splitting and stabilize it just once, right, and especially a vertical Heegaard splitting that's not flippable, which it usually won't be, and then you stabilize it just once, then it becomes flippable. Okay, and here's a very lousy picture that doesn't tell you anything, so I haven't yet drawn the right picture. Let me just describe to you what you would do. Because what you would do is you'd sort of one by one flip the exceptional fibers to the other side. And that's something you can do as long as you have one stabilization. If you have one I'm almost done, by the way. If you have one stabilization, then you say, okay, somewhere here I have a solid torus neighborhood of an exceptional fiber, and it lies in one side of the Heegaard splitting, right? And now I get to stabilize. I stabilize the Heegaard splitting and I get to stabilize it wherever I want, right? That's not supposed to make a difference. And so I stabilize it by drilling a little arc, unknotted arc, out of this solid torus neighborhood of the exceptional fiber. I do that away from the exceptional fiber, but I just kind of drill it out. And then what I do is I have this little removed arc, and I can think of really just that arc, first of all, has two endpoints. I pick up one endpoint and I kind of wind it around the boundary of that torus. I wind it around until it's exactly parallel with the exceptional fiber. And then I kind of pull it across itself and have this little arc connecting from the boundary to exactly a copy of the exceptional fiber. It looks like the exceptional fiber is winding around twice, but really what I want to say, the exceptional fiber is just some sort of torus knot, whatever it is, right? I can run parallel to it. I can create this little sort of wand that goes from the boundary of this solid torus neighborhood of the exceptional fiber, and then along the exceptional fiber. And then when I remove a neighborhood of that structure, then the exceptional fiber is now on the other side. Right? Okay, and then personally, I just happen to know, oh yeah, and then if I looked in the manifold I get from actually removing that exceptional fiber, I have a Heegaard splitting that has genus 1 too many, so I know it's stabilized, so I can kind of pull the stabilization to be elsewhere now, and that allows me to work on the next exceptional fiber, et cetera, and that way, one by one, I can just kind of pop the exceptional fibers to the other side, and then once I've pop them all over to the opposite side, then again, because of what I know about Heegaard splittings of Seifert fibered spaces with boundary, I know that I've exactly flipped the Heegaard splitting again, once I've stabilized it once. Okay. All right, that's all I have to say today. So I hope you enjoyed this little foray into this idea of flipping Heegaard splittings, especially in the context of Seifert fibered spaces. And I know some of you have seen different parts of this talk at different times, and I hope you enjoyed it.